Okay, so one example that you might see is trying to find the region or the electric field in the region between two charged particles. So we have a positive 2 charge here and a positive 4 charge there. So if I were to look at a point directly in between them, what's the electric field at each point? Now remember, electric field is a vector, right? So electric fields from positive charges point away. And so what I'm going to show is I'm going to show that there is an electric field. We'll call this A, we'll call this B. Electric field A is going to point to the right. It points away from a positive. Electric field B is going to point to the left. I'm going to draw it twice as large because what I know is I know that my equation for electric field. Now these are electric charges that are creating an electric field. So this would be using the equation E equals KQ over R squared. How would I then find my net field? Well, I would find electric field of A is going to be KQ over R squared. That's going to be K 2Q. Now my R is going to be that, where that's going to be 1 squared. So that's simply going to be 2KQ. Electric field of B would be KQB over R squared, that'd be QA. K 4Q over, again, 1 squared, which is going to be 4KQ. Again, Q, doesn't matter what the size of this charge is, we just know that this one is twice as big as that one, okay? So the net field, again, we can't really say one's necessarily positive or negative because electric fields and charges and all that stuff, the negatives don't really mean left or right all the time. So what I have to do is just look at this. Well, those two are going to cancel each other out. And so I get my electric field net would be 2KQ, right? Because we're going to have 2 to the right, 4 to the left. So my net is 2KQ to the left. That's going to be my final answer. All right, there is a region where the electric field would be 0. All right, so let's figure that out now. So this example is going to work through, okay, can we find the position where the electric field is actually 0? Again, these are the charges that are producing the electric field, so we're going to use this equation. R squared. We know that distance plays a factor, right? And it actually plays a bigger factor than the size of charge because it's squared. So what I know is there's going to be some region here, might not be the best way to represent it, but there's some region here which is going to have an electric field of 0. That's because the bigger charge here, along with the bigger distance, is going to cancel out with the smaller charge and the smaller distance, where those two are actually going to be the same. So here's what we're going to do. We're going to call this length R, and then we're going to call this length 2 minus R, because my total length is 2 meters. So then, what I know is I know that EA plus EB equals 0. The sum of those two fields are going to be 0. So then that tells me that EA basically equals EB. Again, positive or negative, it's kind of tough here because of the electrostatics, but we know that those two have to be the same. So how can I find that? EA is K 2Q over R squared. EB is going to be K 4Q over 2 minus R squared. Right? Now here's where not using numbers right away can actually be somewhat of a benefit. Okay? We have this equation, we know that they're equal. My K's cancel out. That's nice. My Q's cancel out. That's also nice. So what I have is I can now simplify this as saying 2 over R squared equals 4 over 2 minus R squared. And now all we have to do is a little bit of algebra to solve for R. I'm going to cross multiply. I'm going to bring it back up here as well. Just a little bit easier on myself. So we're going to do 4R squared equals 2 minus R squared. Now what I can do is this, obviously it's going to get a little ugly here, but I can FOIL this out, right? And from that, I'm going to 2 minus r times 2 minus r, and I can work through that process, and I'm going to end up with 8 minus 8r plus 2r squared. So I'm going to get 4r squared equals 8 minus 8r plus 2r squared. I can subtract the 4r over to the other side, and I'm left with negative 2r squared minus 8r plus 8 equals 0. What you can do then is you can solve for the values of r using our quadratic formula if we need to. I'm not going to go through that. That's just going to take too much time for us. But we can see how we can set this problem up. If we knew numbers exactly, it would be a little bit easier to actually work through. Another example would be using this scenario where we have now an electric field which is indicated as pointing to the right. We have a field of 20 newtons per coulomb, and we have a force on a charged particle to the left of 5 newtons. Now, what we're asking to find is just what's the charge on Q. So what I can do is I can use our equation E equals F over Q, and again, that's only for a charge that is within an electric field. I can then solve for Q by finding force over field, and my charge then is going to be 5 over 20, or 0.25 coulombs. What we want to know then is this a positive or a negative charge? Remember that the electric field points in the direction of the force on a positive charge. So because we see that the force is to the left and the field is to the right, that tells us that this would be a negative charge within that electric field. The only other thing that I wanted to go through was just 2 special circumstances that we have with electric fields. The first one is if we have a conductor that becomes charged. So we have positive charges all around this because it's lost all of its negative charges. Well, the electric field would be pointing away, this, and on the inside, the E on the inside, electric field on the inside would be 0. It doesn't matter where you are in that conductor, if you are within it, the electric field is actually 0. So that's one special circumstance that I wanted to go through. Another one is if we were to produce something called a parallel plates. We'll go through this a little bit more within the class. But what that does is that creates a region on this side which has positive charges, and on this side which has negative charges. What we get in this circumstance is the electric field is constant within those parallel plates. The density of the field lines doesn't change. So no matter where you're at in this, between these parallel plates, you're going to experience the same electric field. Doesn't matter if you're at point A, at point B, at point C, they're all experiencing the same electric field. The only difference would be once you get towards the edges, right? So there's fringe interference there that we'll talk about, but otherwise, inside a parallel plate, the electric field is always going to be constant.